My name is Rebecca Kleinberger. I'm an assistant professor at Northeastern University, where I direct the Interact Animal Lab. I will present my team's project called No More Angry Bird, investigating touchscreen ergonomics to improve tablet-based enrichment for parrots. This work is a collaboration between Northeastern University and the University of Glasgow, and with Ilyena Hirskyj-Douglas, Jennifer Cunha, and Meghan McMahon. Touchscreen devices have become ubiquitous in human day-to-day lives, but their use also extends beyond humans. There is a long history of animals using touchscreen in various contexts. For the pigeon project in 1940, Dr. Skinner housed pigeons inside missiles, where the bird would control from within by picking on targets on the screen. For cognitive and behavioral research, touchscreens have been used to explore navigation, memory, and preference testing in animals. More recently, touchscreens have started being used for animal enrichment, initially mainly for primates, but also for pets and in research context. Not all animals are physically capable to trigger classic touchscreen sensing technologies. Most existing cases involve the use of custom and personalized hardware specifically made for animals. However, there is great scalability potential in adapting off-the-shelf mobile devices for animals. With advanced cognitive abilities, keen visual perception, and adeptness to engage with capacitive screen using dexterous tongue, parrots are uniquely positioned to benefit from off-the-shelf touchscreen systems. However, even if they can use the hardware, current human-centric touchscreen interaction and software standards may not optimally cater to the bird's tactile affordances and ergonomic needs. This motivates this research and our three research questions. First, do pet birds touch the screen the same way humans do? Second, can target distance and size be optimized for bird users? And third, can Fitts law, a cornerstone of HCI, predicting a linear relationship between movement time and index of difficulty, be validated with pet birds? Fitts law is particularly relevant in HCI when designing pointing devices like a mouse, stylus, or touchscreen. It predicts that the movement time required to rapidly move to a target area is a function of an index of difficulty, corresponding to the ratio between the distance or amplitude to the target and the width of the target. It has been shown to apply in various conditions, controlled with hands, eyes, feet, drone, or underwater, and with various populations. In the current project, while we do not claim that Fitts law directly applies to parrot, we use this model as a framework for assessing performance and measuring the speed and accuracy of target selection tasks. We also do not claim that the proper evaluation condition for Fitts law on motor command can be fulfilled in the context of pet parrots, but we use our data to assess the usability of the model in the avian context. To assess this, we explored touchscreen interaction in pet parrot on off-the-shelf devices. First, we ran an initial survey of parrot participants to gain insight into the current usage pattern and inherent challenges of touchscreen with their avian companions. Secondly, we developed an initial version of a target touching application that we refined through a pilot study with 5 birds. Third, we ran a 3-month study with 20 birds, 17 of which completed the entire protocol. And finally, human caretakers filled up a post-study questionnaire to share their perspective on the experience of their bird. The initial survey and our pilot experiment led to several design choices for the main study. There's the implementation of a consistent setup guideline, the addition of sound effect for motivation and an exit button for agency, limitation of the number of touches, series, and session to avoid fatigue and maintain engagement. We identify 4 target width and 4 amplitude based on the observed difficulty for a total of 16 different amplitude width combinations. And we observed that birds often multitap, so we implemented a 300 millisecond multitap threshold to avoid missed target based on multitap. Taps less than 300 milliseconds apart were recorded but ignored for the purpose of target selection. We recruited 20 remote participants living in family houses across the US and who stayed in their regular environment during the study. The caretakers had prior training working with animals, and available time to facilitate sessions. The bird had prior experience with balloon pop type games. 17 birds fulfilled the requirement to enter the testing phase and completed the entire protocol. Custom target testing application was adapted for the FitTouch app from Scott McKenzie's lab. Participants were guided through touching series of dots that each started with a central blue target to tap to normalize the initial tap location. Performance data included movement time, touch location, missed target, finger pressure, when available, were automatically recorded and sent for analysis. All participants used the same device, and target and touch location were measured in density-independent pixel units relative to 160 PDI screens. This type of ergonomic studies necessitate a certain level of ease in interacting with the interface, and the subject best effort to complete the task as fast as possible. As instructing animals to complete the task quickly is challenging, we set up our protocol into first a learning phase and a testing phase. The first part of the learning phase, bird received a treat for each touch, accurate or not, and a bigger treat for successful hit. For phase 2, we engage them to touch several dots in a row. And for phase 3, we encourage them to complete the entire sequence. The testing phase was similar to phase 3. For the transition from one phase to another, we were not looking at absolute score, but stable score for each bird. The goal was to meet the bird where they were, to have a better picture of the diversity of capabilities. In the long term, the goal of this research is to allow for more parrot-adapted interaction with technology to provide agency and enrichment by controlling interfaces more ergonomically adapted to them. However, we do not recommend for system to be used in isolation or in replacement of in-person social and environmental enrichment. And we believe that technology can best benefit parrots in a social context, and to the extent that it enriches and reinforces the bond with their caregivers as well. We leverage contra-free loading, where animals prefer to work for food while it is also freely available. Birds were free to leave or disengage at any time. The study yielded 3 types of data. First, videos of all the interaction sessions, then touch data collected automatically by the application, and the post-study questionnaire filled by participants. We cleaned the data before processing, and specifically for fit slow validation, we excluded all segments where birds were distracted and not fully focused on task. We observed that capacitive sensing does not always recognize when the bird touches the screen, even with the highest sensitivity parameters. This might be due to the relative dry tongue of parrots. We also noticed that most parrots engage in multi-tapping, defined as 2 or more taps within 300 milliseconds. For birds, about half of taps were multi-taps, mainly double taps, but also triple, quadruple taps. The maximum number of taps recorded as multi-tap in the 300 millisecond threshold was 41. And the minimum time recorded between taps was 7 milliseconds. Birds had a higher drag than humans. Based on one human-bird participant pair alone, we compared the bird and the human touch pressure. Within this pair, the bird pressed the screen less strongly than their human caregiver. When looking at hit rate, birds successfully pressed within the target about 50% of the time, which is higher than pure random, which would be the surface of the target compared to the full surface of the screen, about 2%. We also observed a high variability, with medium bird doing better on average. We see a correlation between size of target and hit rate, but not with distance between targets. This suggests that the bigger the target, the more the bird taps successfully. However, this increase in successful hit could be due either to enhanced precision by the bird or simply by a larger target area available for touching. For a more in-depth understanding of tap accuracy and to understand optimal target size, we explore the distribution of tap location compared to target coordinate. We centered our data around the intended target location to measure the deviation from the target in horizontal and vertical location. We observed a 5-angled star shape in the tapping pattern, suggesting that some taps occur in the trajectory between the previous and current target. And this was confirmed with visual observation, where the bird tends to tap in the previous target location before noticing that the target has moved. Our data do not validate Fitts' law. We do not observe the linear relationship between movement type and index of difficulty. One possible reason is that the bird were not touching as fast as possible. This inadequacy of Fitts' law suggests this potential overhead in movement time, rendering them invariant to the target amplitude. Reviewing the video led to identifying a touch and retreat motion, where the bird appeared to take some distance from the screen between targets to better see where the next target arose. The result from our survey showed that all human participants believe that there is potential benefit for their bird to using adapted system on tablet. Most common cited benefits include cognitive enrichment, mental challenges, and bonding with caregivers. In terms of risk, participants mainly mentioned potential damage to the tablet, overstimulation, and potential physical harm. Human participants also highlight the need for optimization. Most reported enthusiastic engagement from their parrots, although some displayed waning interest over time, possibly due to the repetitive nature of the task and the study duration. Participants mainly found the study enjoyable and enriching for their birds. The initiative was also viewed as a means to enhance the bond between caregiver and their parrot, with one human participant reporting that this brought their bird and themselves closer. We propose possible design guidelines for designing parrot-specific enrichment on tablet. First, the important potential of tablet-based parrot enrichment, and the inadequacy of existing human system and the need to design for their unique bodies, the need for personalization, continuous accompaniment, social context and humans in the loop, and ethics and safety considerations. Our findings highlight the need for more optimal bird-sensor interfaces, the pronounced multi-tapping behavior and need for threshold, the greater effectiveness of larger target over closer proximity, and the recommendation to not use such system in isolation, but as a potential for bonding. This study opens the door to leveraging technology for animal enrichment and agency.